Okay, so welcome everyone to today's HAO Colloquium. And the speaker is Matthew Brown, and he completed his PhD entitled Climate Change in Space, the Impact on Space Debris at the University of Southampton in 2023. And he's now a research fellow in the Serene Group at the University of Birmingham as part of the SWIMMER program, improving and operationalizing the ENEAS model, the UK Met Office's Space Weather Operations Center. And his research interests cover the thermosphere, low Earth orbit, space debris, space weather, and space climate. And so today he will give a presentation titled Days to Decades, Forecasting Space Weather and Climate in the Thermosphere. So Matt, if you want to go ahead and share your screen.
Yeah. There we go, and then if I switch to it, perfect.
Yeah, it looks good, so go ahead.
Awesome. So yeah, I've called it this Days to Decades moniker because I'm looking at forecasting the densities on both very short timescales, so just the days, but also very long timescales of decades, looking at climate change stuff as well. And it's two different ways of modelling the thermosphere, which I'll be talking about. Oh, I should add, I did my PhD with Hugh Lewis at Southampton, and Andrew Kavanagh and Ingrid Nossen were my co-supervisors at the British Antarctic Survey. And now I'm at Birmingham working with Sean Elvidge and David Temmons. So I'm sure everybody's aware, but I like showing this graph just because it links the two together, where we've got neutral atmospheric density and it decreases rapidly with altitude. And then when we're talking about the thermosphere, that's usually above about 100 kilometers, and that's where we start to think of space. But within the thermosphere, we have all of these orbiting objects in low Earth orbit. So SpaceX Starlink constellation at 550 kilometers, space station at 400 kilometers. Permeating throughout is space debris at all sorts of different altitudes. And another thing as well, I've talked about climate change very briefly, and I'll talk about it later on. But when we think about it, usually we think down in the troposphere, we talk about global warming, but it's only a very small part of the atmosphere, and it permeates throughout. And I'll be talking about some of the impacts on the thermosphere later on. So I'm going to lead with one equation because this just governs everything, and it's the only equation I'll actually show. But this is the force due to atmospheric drag acting on a satellite. So it's proportional to the atmospheric density, which is incredibly low up in low Earth orbit. But it's also proportional to the coefficient of drag. So that's dependent on the shape, the materials, and the geometry of the satellite itself. So how pointy it is, how well it can actually slip through the thermosphere. It's proportional to the area to mass ratio, but it's also proportional to the velocity squared. And that's key because when we're going up into low Earth orbit, things are traveling incredibly quickly, over 7 kilometers per second. So although we're traveling through a less dense medium up there, because we're traveling much higher speeds, we actually get an appreciable atmospheric drag at those altitudes. And this is all of the objects orbiting in space. So you can pick out the geostationary ring in the top left. There's a few objects going down towards low Earth orbit, but then over 70% of the objects, that might be even higher nowadays, about 80% of those objects are in low Earth orbit, so within the thermosphere. They're experiencing atmospheric drag, which is why it's key to quantify the atmospheric density as well as we can. So we have operational satellites. So for example, Hubble here, if there's a change in atmospheric density to lower it, then that's great for operational lifetimes because they don't need to carry as much fuel to maintain their altitudes, for example. But when two satellites collide, you end up with space debris, and the exact same rules are governing both. So if the orbital lifetime of a satellite increases, for example, the same is happening to the debris. And LEGO is a really good analog for space debris because when it breaks up, you have loads of different sizes and shapes of all of the pieces of debris. So in the top left, we've got rocket bodies, for example, the big bulky things, which still have considerable mass and size. But then down towards the bottom, we've also got flakes of paint and really tiny things. as well. We've also got wires and pieces of metal foil and all sorts breaking off. So it's really diverse what can be space debris. And this is just the number of objects over time, just to reinforce that point of how many objects there are in LEO. So as you can see, going forwards, we get an increase over time. Over 70% is in LEO. When you look at MEO, GEO, Super GEO, it's very gradual with time because there's not many collisions. But then when you look at the LEO one, the purple line, you're getting large spikes, and that's from major collisions or fragmentation events. So the first big one, the 2007 one, that's a Chinese anti-satellite test. That happened at a fairly high altitude, which means there's not much atmospheric drag. So those objects, as soon as they're created, they reside there for a long time. But then if you look ever so slightly afterwards, I think it's 2008, start of 2008, there was another fragmentation event, but that happened at a much lower altitude. So those objects experience atmospheric drag and are removed from the debris population rapidly. Then 2009 is another big one to pick out. That's the Cosmos-Iridium collision. That's two fully intact satellites colliding with each other. One was operational, one wasn't operational. There's some discussion on how this occurred. But they hit each other, created a massive amount of fragments, and it was fairly high up. So again, a lot of those fragments are still residing within the population even now. And then going forwards in time, the most recent large spike was the 2021 Russian anti-satellite test, which created a lot of fragments, again, at a high altitude. And then some of the size and numbers of debris, just to drill down into that a little bit more. So far I've been talking about trackable objects. That's objects larger than 10 centimeters in size. They're good because we can track them, so we know where they are. And then we can propagate that through atmospheric models using orbital propagators, those kinds of techniques to work out where they're going to be in the future so we can avoid them. And that's good because these objects, if you collide with them, they're catastrophic. So they're going to create massive fragmentation events and completely destroy any operational satellite or big piece of debris that it collides with. But then the interesting range is the 1 centimeter to 10 centimeter range, because this is untrackable. We don't know where they are. We don't know how many there are exactly. I've put 1.1 million objects here, but actually that range is up to about 3 million. But these are the objects which are highly damaging to satellites, so they can completely knock them out, or they can do a lot of local damage. So if they hit in the right place, they can still destroy a satellite. And then even smaller than that, so smaller than 1 centimeter, so about the size of a fingernail, you get 130 million objects which don't do much damage to a satellite, really. So I've got a panel of the Hubble up there, and every little yellow arrow is just a little pocket mark where they've hit. But there's so many objects and so many collisions that sometimes they're going to hit in exactly the right place to do exactly the wrong thing and break a cable or break an electronic connection. So there's still something to consider and try and protect against for operational satellites. And just to drill down on the untrackable stuff, just to demonstrate the kind of energy and impact these pieces of debris can have. On the left-hand side, we've got a 1.2 centimeter size steel ball bearing, and that was fired at 6.5 kilometers per second, so slightly slower than orbital velocities, at a 18 centimeter block of aluminium. And as you can see, it hit that, and because it's got so much kinetic energy, it actually causes a splash within the aluminium block itself, and it treats it like a fluid for that brief millisecond whilst it's impacting. But it's not just that. You have the initial impact, but then there's a shock wave which travels through the medium, and you can see at the bottom there, it's cratered out the bottom. So if that hits a satellite, it's not just the immediate place which is impacted. There'll be shock waves ricocheting through the satellite, which can cause further damage. And on the right-hand side, we have two pictures. So the first is just the solar array of Sentinel-1A as it was deployed. And then shortly after it was deployed, I believe, it was hit by an object about the same size as that steel ball bearing there. You can see the crater that it leaves in the solar array. It breaks that part of the lighter solar array, then all of the electronic connections are broken. So it can generate less power, but also it's imparted its momentum to the satellite, and that caused the satellite itself to start rotating. And that means all of a sudden, the solar panels are no longer pointing towards the sun, so it's losing power through that. Its radar dishes and communication dishes are no longer pointing towards the ground, so it's no longer communicating, and you can't communicate to the satellite to understand what's gone wrong. So although it's only a small impact and it's done relatively little damage, it's a case where you can lose the satellite completely, just because lost communication, you're losing power, it's in a dangerous, precarious position. And then one other thing that I wanted to highlight was error ellipsoids. So this is how people think about when they do orbital propagation. If two of these are intersecting with each other, then you usually want to do a collision avoidance maneuver to try and avoid colliding with another trackable piece of debris or another satellite. But you can see that these are elongated along the path of the satellite, and that's because the largest errors are actually in track of the satellite's velocity, and that's caused primarily by the uncertainty in the atmospheric drag and trying to quantify that ahead of time, so then we can work out where it will be further on later in time. And that leads into the days side of the forecasting. So this is days space weather forecasts with Aeneas. On the right hand side there, we've got Aeneas versus Turnus. And I'm not sure which one is Aeneas, but I think we've agreed that it's the one on the ground actually at this point. Not very good on Greek art. Aeneas is quite interesting. I've just brought up this equation again because one thing that other thermospheric models in particular have trouble with is disambiguating between atmospheric density and the coefficient of drag in models, because one of the main observations that we have of thermospheric drag is actually by the satellites themselves, understanding how they're moving and how their semi-major axis, for example, is changing over time. From that, we infer a atmospheric density that they've experienced. But one of the problems is actually quantifying that coefficient of drag for a satellite and trying to disambiguate those two. So often they're combined together. But yes, I haven't brought that up yet. But that's something just to keep in mind for these next few bits. So Aeneas is the Advanced Ensemble Networked Assimilation System. So it's a per-atmosphere model. It uses TiGCM as the background model. So we've got full chemistry, full physics, full dynamics in there. And then we're pushing it with data assimilation. So we're assimilating observations, which I'll talk about in a minute, through the local ensemble Kalman filter. And that means that we can take the background model, we can push it towards what the observations are telling us is the actual current state of the thermosphere. So we produce a nowcast. And then we can take that initial state of the thermosphere and propagate it forwards using the numerical physical part of the background model, so TiGCM, to provide forecasts. And then because we're also using an ensemble Kalman filter, we have an ensemble of possible states of the thermosphere, and that allows us to produce uncertainties on our forecasts. And they don't have to necessarily be Gaussian, so sometimes you get non-Gaussian errors, which you can pick out. And I've said here that it's running operationally at the UK Met Office. It depends on your definition of operational. At the moment, it is running in a testing place, proving that it is operational. But by the end of this year, there'll be output available, and it will be truly running operationally at the UK Met Office. So part of the Met Office is the Met Office Space Weather Operations Centre, which I just wanted to highlight in case I bring up the word MOSWOC often. They've been focusing a lot on the sun, but then in the past few years, about 5-6 years, there's been the SWIMMER project, which is Space Weather Instrumentation, Measurement, Modelling and Risk project. And that's been a research to operations kind of program. So I've taken a lot of models from academia. So there's Huxley, for example, modeling solar wind. and other models that I can't remember off the top of my head right now, but they've moved them into their operational suite, so now forecasters can use them and they can provide forecasts to end users, so satellite operators. There's also ionospheric products that we're working on which go out to airplane operators, for example, trying to work out what are the best radio frequencies to use to communicate with airlines, that kind of stuff. So it's been a very big push of the research and academia models into actually using them operationally, providing output, and then feeding through. So I talked about some of the observations which are going into Anais and providing us with that nowcast. So some of the ones which have been used in the past are electron densities through slant tech, particularly from GNSS satellites. That's the major one that we use. We can also get vertical tech from altimeter satellites. A lot of those are just integrated electron densities along the line from the satellite to wherever it's being picked up on the ground, for example. But then we can use ionosondes to get vertical profiles over different parts. This is just all lots of information feeding into the Ensemble Kalman filter, so we can provide as good a initial state as possible. We also use radio occultation, which I'm not too familiar with. But one thing that we've been switching towards as well is looking at neutral densities. So from CHAMP, gray swarm, pod-derived densities, but also two-line elements, which I'll talk about more in a minute. But when I discussed earlier about the coefficient of drag and density disambiguation problem, using the ionosphere observations is actually quite a clever way of getting around that, because we're using the ionospheric observations to characterize the ionosphere, which allows us to then understand what state the thermosphere is in through that background TIGCM model. And then we can get our neutral densities through that. So we've completely avoided the coefficient of drag problem. And then when we're feeding in the total neutral densities from other things, we can actually use that initial state from the ionospheric parts to give us a first guess on the coefficient of drag for all of the satellites, and then use that to tweak things around. So one of the problems that we had originally was that TIGCM only went up to about 400 to 700 kilometers, depending on solar activity conditions. We've had to extend that a lot higher because satellites are operating at those altitudes and they'd like to know what the densities are up there. So we've been extrapolating using Bates-Walker profiles, which I've shown on the bottom part there. Basically, it just extrapolates each of the individual number densities up, and then we sum them to get the neutral density overall. We've gone up to 1,250 kilometers. That's just a requirement that's been set because we'd like to provide densities to the OneWeb constellation, but there is not much of a reason why we couldn't go higher if required. Oh, and one other thing I was going to mention was we are currently using TIGCM version 2.1, I believe. But shortly after this was implemented, I think it was a couple of days later, TIGCM version 3 came out. So we're now looking at including that, because that actually goes up to much higher altitudes just within the model itself. So TLE assimilation. So this is quite a nice data set for neutral densities, but it's got its problems as well. So TLEs are two-line elements. So it's just two sets of 69 characters which give a position of a satellite at a certain time, at a certain epoch. And then you can use two of those to work out how much a orbit has changed, and therefore pick out that neutral density again. They're really good because they're public and they're available for all tracked objects, but they're incredibly noisy. So on the top right there, I've got a group of 4 examples. So in each group, there's 3 different plots. So the first one's semi-major axis, Below that is eccentricity, and below that is inclination. So in the top left one, we've got a well-behaved set of TLEs for a satellite, in this case, Iridium 33, where it's a little bit difficult to pick out, but there's a few outliers which are easy to just remove in red. And we want to remove those because they will result in fake density changes. On the top right, then, we've got a satellite which is well behaved, but then suddenly it becomes incredibly noisy for some unknown reason. In the bottom left of the set of 4, we've got a satellite well behaved, but then all of a sudden the signal splits in two. So it's a misidentification where it's flickering between 2 satellites and it's not sure which one is which. And then on the bottom right is the one that we really want to remove, which is the maneuvers. So this is a satellite which is constantly increasing its altitude in time. But we want to remove those because that's a lot of energy being placed. And it's not just increases in altitude, it's also decreases that we're trying to move out, as well as in or out of plane maneuvers, so changing the inclination, for example. So the way that we're doing this and trying to do it in real time is with the TRUST algorithms. This is tracking real-time unusual satellite trajectories to give it a nice initialization or acronym. So that uses DB scan, so density-based spatial clustering. So with this smiley face, we're going to start off with 1 point. We then draw a circle around it. We work out what other points are within that circle, and then we cluster those together. And we just keep on repeating that with all of those different points until we run out of points which we can cluster together. And then we move to a new point. So it will be to blue, for example, do the same and pick those out. So that's the general gist of the DB scan algorithm, but then we've applied it to the TLEs by doing it with, instead of just a circle, we do it as a box across semi-major axis, eccentricity, inclination. We define the size of the box depending on the kind of change that we would see in those orbital elements within the period between the TLEs that we're seeing. And that means then that we can start picking out different maneuvers. So we've got different colors as we change between maneuvers, but that allows us to still use that satellite and all of the information between the maneuvers. And it also allows us to pick out outliers. So we've got still red dots in there. And although they might not look like outliers in one particular orbital element, there'll be outliers in other ones. And this is an incredibly good algorithm to use for our real-time model assimilation, because it doesn't rely on many previous points. So we just need to draw a box around the current point, pick out the last 6 or 7 or so TLEs and see if it's clustering with any of those. And we just keep the information for those ones. And then as a new TLE comes in, we compare with that. We can drop off the oldest TLE and we can just keep repeating that. And it becomes quite a nice way of working out outliers or whether maneuvers have occurred without much actual computation being done. So we can move straight on to deriving the densities and plugging those into NAS. So now I'm going to switch completely onto the decades part of days to decades. So this is the work that I did and I'm still finishing up on my PhD. So this is the CO2 impact on space climate in particular. And on the right-hand side there, I've just got the stripes which are commonly used, and I've tried to apply them to the change in temperature within the thermosphere, but it gets a bit tricky removing the solar cycle impacts. So it hasn't come out brilliantly. So it was a very quick primer for the impact that CO2 has on the thermosphere. So top left there, we've got the CO2 concentration with altitude. So at ground level, this is for the year 2000, I think, 370 parts per million at ground level. That's roughly a constant concentration as we go up to the homopause, so about 80 kilometers. Because it's very turbulent, well mixed, the concentration stays the same. But then above that, we start getting gravitational separation. So the heavier molecules are settling down towards the lower part of the thermosphere or upper atmosphere. So we get an exponential drop off with altitude, but there's still quite a substantial amount of CO2 in the lower part of the thermosphere. And then the right-hand side there, we've got a graphic showing the lower and higher atmosphere. So CO2, this is the greenhouse effect. It's absorbing energy either from the sun, for example, or from collisions with other atoms and molecules around it. It's then re-emitting that energy either through collisions with other atoms and molecules again, or through infrared radiation. If that infrared radiation is emitted, because it's very dense in the lower atmosphere, there's lots of things to recapture it. Has a short mean-free path. All of the energy is trapped, the greenhouse effect. In the higher atmosphere, you get the exact same mechanisms. So CO2 is still gaining that energy from the sun or from collisions, but it's a lot less dense in the upper atmosphere. So it's less likely to collide and lose its energy. So it's more likely to emit. It's hit as infrared radiation. That infrared radiation then escapes because there's not many things to trap it. So you lose heat from the locale, and it either escapes out to outer space or back down to the ground. And that means that you get a cooling effect in the higher atmosphere. So although it's the exact same mechanisms as the lower atmosphere, where you get global warming, in the upper atmosphere you get global cooling. And then, like when you put a balloon in liquid nitrogen, as it cools down, it contracts down in size. And that means then in the bottom right, when you have a satellite at a fixed altitude, the thermosphere will contract around it, and it will end up in a less dense region of the thermosphere, even though it's at the same altitude that whole time. So that's a very quick primer of my way of thinking about it. There's other ways where you can think of energy budgets, for example, but I like this one in particular. So in the literature, this was first identified for the mesosphere and thermosphere in particular by Roble and Dickinson back in 1989, and there's been lots of studies since then, both studies observationally and modeling wise. I've tried to collate them here into this singular graph. You can see a wide variation. A lot of that is due to solar activity, which I haven't accounted for in this. But the one thing that all of those studies agree on is that there's a decreasing density trend above 40 kilometers altitude. And it's quite a substantial density change per decade. But one of the things in particular is that it's a percent per decade change rather than basing it on the CO2 change, which is what is actually driving it. And that's one of the things that I wanted to try and work on the PhD, so then I can look into the future and start tying things to what the CO2 is going to do in the future, what kind of density changes happen in the future. So that's what I did. I used Cesium with WACM-X. I modeled the thermosphere by having CO2 concentrations from ground level. I showed that concentration profile earlier. I scaled everything to what matched the ground level CO2 concentration in steps. I did it for low solar activity, high solar activity, so 70 solar flux units, 200 solar flux units. And then I've picked out just some altitudes here, so 200 through to 500 kilometers. And you can see the density reductions are largest under low solar activity. They're larger in magnitude at higher altitudes. And one other thing that I've done is taken everything as a density relative to the year 2000. And that's just so we've got a starting point, but also then so you can use them as a scaling factor to empirical models. So like NOL-MSIS 2000. If you say that is a good representation of the year 2000, then you can use this to apply some scaling factors onto that model. Keep the speed of NOL-MSIS, whereas WACM-X takes a long time to run. But account for the CO2 trend. Another thing to pick out in this graph in particular is about 460 parts per million. There's a bump in the density reductions. I've never been able to work out what this is due to, but it happened in both runs separately. It doesn't correlate with any of the inputs, so I'm not sure if it's some mechanism that I couldn't pick out within the thermosphere which was causing this, or I'm not sure. I just always highlight it. So one of the problems that I had in my PhD was I didn't have much computing time, so I was very limited in what runs of WACOMEX I could do. So I did a low solar activity run, which is the red box, a high solar activity run, which is the orange one, varying the CO2 concentrations. But then to try and understand the impact which F10.7 has on the trend, rather than just having 2 points, I also did a fixed CO2 run of about 650 parts per million. But I varied the F10.7 in a couple of more steps, just to try and get how the F10.7 affects it at a middle-ish CO2 concentration. And then from there, I filled in the gaps just simply through linear interpolation, just to get a nice grid. And this is for 400 kilometers altitude, but the trend is dependent on F10.7, CO2, and altitude. So I've got nice grids describing all of these. I should say as well, this paper has been accepted and published, and I forgot to remove submitted, sorry. So I talked about actually linking it into the future through the CO2s going out into the future. So I did that in this case with the shared socioeconomic pathways. So this is CO2 concentrations going out into the future, which the Intergovernmental Panel on Climate Change released, so the 1.5 degrees Celsius group. In blue, we've got the best case scenario, so CO2 emissions peak, and actually CO2 is removed from the environment, so the concentration drops. In red is SSP 5-8.5, worst case scenario, fossil fuel usage, and then I've picked two intermediate ones. So this gives a CO2 concentration going out in years, and what I can do then is take a example solar cycle. So here I repeated solar cycles 23 and 24, I believe, just going out into the future. And then I can pick out what the CO2 is, what the F10.7 is, and then I can start plotting what the density is going to do out into the future under these four scenarios. One of the things to point out here is that SSP 1-2.6, when CO2 is actually removed from the air environment, the thermospheric densities start to recover as well. One other thing to add as well, just while I remember, these density changes, you see the solar cycle impact. This is applied on top of the order of magnitude change that you usually get due to just density changing by an order of magnitude from solar minimum to solar maximum. So what impact does this have on the space debris environment? So this is my little flow chart of how things work, because it's a nice way of showing it. So I've shown higher CO2s give you lower neutral densities. If you have a lower neutral density, you get less atmospheric drag on a satellite. Less atmospheric drag leads to a longer orbital lifetime. And then because you have that longer orbital lifetime, there's more chance to collide with other objects during that lifetime. More chance to collide then means that you're going to get more collisions, more fragments generated, which means there's more objects for you to collide with. And that means that there's going to be more collisions happening, and then you get a feedback loop. So although you've got a linear start to this flow chart, you then get a feedback loop at the end. So then how I modeled this was I created a debris model. So this is Brad, the binned representative atmospheric decay model. It bins objects by semi-major axis, eccentricity, inclination, and mass. So we can define the orbits of the object and also the size of the object. This is quite nice because we're binning objects, we can represent loads of objects with just one object, and then everything is scaling by the number of bins times the number of bins rather than how many objects you have, because it's an n-squared problem. So then when you get out to the much later times where not many objects have been removed by like 2100, say, the model is still just as fast as when you at the very start when there's not many things happening. And I've just got a flow chart there of what kind of things are included in the debris model. So just as a very quick rundown, we've got the atmospheric model with all of the things that I've discussed being put in to work out how the satellites are changing through the orbital propagation. That then allows the bins to move around, and how many objects within each bin and how they move through the bins. We can then feed in launches into those bins, so how many objects are being added at each time step. We're then doing collision prediction, so that depends on how many objects are in the bins, how likely 2 objects in each orbit of a bin are to collide with each other. If we decide that 2 objects have collided, we need to fragment them. So we have the NASA standard breakup model to do that, where we can just add in 2 objects, we can sample a velocity and create the fragments and the sizes, and then rebin those back into the population. And then we just feed that through, and we keep doing that for each time step, and we can feed it through into the future. So this is an example run here, which I've just picked out. So we have, because you can have a very large collision early on, for example, say in the year 2010, that will set up the population with a lot more objects and result in a lot more objects later on. So you have to do a Monte Carlo, you have to just run it multiple times. Here I've just done 64, for example, and then take an average. And another thing here is that I've taken an initial population with perigees below 500 kilometers. And I purposely started with the year 2000 so that I could remove all of the constellations. And I have a dead population, so there's no maneuvers happening and things trying to avoid each other. And that was just based on some of the original assumptions of Brad, which I'm now addressing in a second version, which allows me to add constellations and things to interact with each other. So here, this is a control. I've shown the Monte Carlo thing. We can also take statistics, so standard deviations on that. But this is a control. This is just NOL MSIS as the atmospheric model. There's no CO2 trend on here. So then we can apply those density reductions, which I discussed earlier. So one thing to note here is that I haven't currently rerun Brad with the new SSPs. What I'm using is the old RCPs, so the representative concentration pathways, but they're very similar. So I've picked out ones which match the SSPs, which I've shown earlier. So this is Brad under each of the RCPs, so the lowering atmospheric densities. And you can just pick out by eye there that they're actually increasing as you put more CO2 into the environment. But hopefully on this next slide, yes. So I've just divided through by the control here, so you can just pick out the fractional increase over time. So one of the things which I found from this, which I wasn't expecting, was RCP 2.6, so the blue line. Although you get a recovery in thermospheric densities because that CO2 is being removed, the concentration's dropping, because by the year 2050, you've already seeded the space debris population with more objects. That overtakes any recovery that you get through recovering thermospheric densities, which was quite interesting and I wasn't expecting. And that's also, so this is just the dead population, remember, no constellations, and that's a best case scenario. That's 40% of objects that aren't being accounted for in current debris modeling because they don't include the CO2 trends. In the worst case, it's over double what you'd actually be expecting. And I'm hoping to redo this with constellations and a newer population rather than the year 2000 to see what impact that has. So far I've talked about debris evolution and actually modeling things from the start, but this is a different way of thinking about it. So this is some work that I've done with Will Parker at MIT on instantaneous orbital capacity. So the idea behind this is if you take shells at different altitudes, objects are being removed from those shells through atmospheric drag, but things are going in through launches, but also objects falling in from above shells. And the idea is to balance it out so that at any one stage, even with collisions happening, you get a stable population and it's not going to run away and cause a Kessler effect. So that's how you quantify this type of orbital capacity. There's no structure in this, so this isn't a set number which should be aimed for, and we can say we can put all of these satellites into space. This isn't what this is. This is just trying to understand what kind of mechanisms are at play. So we've summed up all of the altitude scales to get this instantaneous orbital capacity, and then we've plotted it with time, and you can see the largest variation is with solar cycles. So as you'd expect, solar maximum, more atmospheric drag, more objects are being removed, which means that you can put more objects up there because they're going to be removed with time. But each of these times is just a snapshot in time. So what is stable at the solar maximum isn't going to be stable at the solar minimum because of less atmospheric drag. But although we've got a large variation with solar cycle, as soon as you add in those trends, which I've been discussing in thermospheric density, this orbital capacity is reducing rather rapidly with time, which is going to be true even if you model instantaneous orbital capacity in a different way and add in structure. So I think I've gone a little bit quick there, apologies for that, but as a very short summary, on short time scales, data assimilation provides a path to forecast neutral densities because you can take those observations, get a nowcast of the current state of the thermosphere, and allow a physical numerical model to run forwards and get your forecast. And then on longer time scales, empirical models don't currently include CO2 trends, and that leads to underestimated orbital lifetimes, and you're missing a substantial trend in space debris models, which then feeds into policy making where you've got that 25-5-year rule, all of those decisions. So thank you.
Okay. Thank you. Very nice talk. Are there any questions? Oh, Mary.
Can you hear me okay? I have a couple of questions. If you go back to your next to last slide where you had the long-term, so yes, that one right there. Your forecast, it looks to me like you're forecasting, I can't see it quite from where I am, but you're forecasting constant maxima of solar cycles going forward. It looks like, but there's evidence that we've passed the Gleisberg minimum and that solar activity will be ramping up over those cycles, and therefore the atmosphere will be expanding. And so that might remediate some of your CO2 effect. So that's something you could take into account, perhaps. Yeah,
that's completely fair. In this case, we were just trying to show the impact that CO2 was having, while also including a solar cycle to try and show that that had the major impacts. But yeah, that's completely true.
And then the second is that there was a recent failure of a Chinese satellite system launch, as I understand it, that's going to be like Starlink type satellites in that kind of orbit. And I've forgotten what altitude that occurred at, but that wasn't part of your study. But where is that in the scheme of things, altitude-wise? I've forgotten.
I want to say it was about 800 kilometers.
Yes.
It was A, it was high up for atmospheric drag, and B, it's before they actually start deploying their constellation in large numbers, which could have an interesting impact. So they could shift the altitude that they're operating at to try and avoid the debris that they've caused at the very start of deploying them. Yeah, it's going to be interesting to watch that and see how that unfolds.
Yeah, I haven't read about any remediation attempts or whatever.
No.
Yeah.
Ling, go ahead.
Yeah. Okay. So Matthew, yeah, it's a great presentation. So I have a question about, for example, in this case, like there's a 100 from 2000 to 2100. So you look at how CO2 basically impact mass density. So what kind of model is used to do this calculation?
What for the debris environment on this slide?
This is not your model, but in your because you also earlier you showed that your calculation. So which model did you use to calculate CO2 increase, the impact of that on mass density, and therefore on the number of space debris?
So we used WACOM-X to work out scaling factors, which we then used on MSIS within, for this particular study, this was the MOCAT debris model.
So does that CO2 like change with like you use parameterization of CO2 like into the future, like a linear increase of CO2, or you just do like a certain number like 400 and then 500 ppmv?
So I did snapshots in time. If I go
snapshots in time, okay, not like the linear. I mean, every year the time varying.
No.
Yeah, I
That's
see.
one thing that I'd like to do and run WACOM-X with each under each SSP scenario as like a transient run with that ramping up CO2. But I just did not have the computational time to do that in the PhD. So we did a snapshot where we took WACOM-X, we scaled the CO2 profile to get what it would be. We also scaled the carbon monoxide because that'll be in chemical equilibrium. We ran it for, I think it was 4 months. I can't remember. We ran it for a spin-up time just to make sure that there wasn't anything strange happening with the densities. And then we just ran it for the whole year, took global means, annual means, and then took relative differences.
So basically the CO2 at the surface, Earth's surface is changed, like for example 600 is 700, and then you run the model for 4 months and then run for 1 year.
Yes.
Okay.
But if I go back again, this CO2 profile, so we basically shifted the whole profile as well. So that also changed the CO2 concentrations in the lower thermosphere at the same time.
So you change it as like a global mean profile. Basically, you put in the global mean average profile. Okay.
Because the problem was when we put it in at ground level and just let it propagate up through the atmosphere, it just took too long to do.
Yeah, take a long time. Yes.
Yeah. And at that point, you might as well do a transient run, which I couldn't do.
Okay. Thanks.
Thank you.
Yes, Matthew, I have a question. Maybe that earlier you already answered that when you addressed Ling's question. So you were not doing the projection, the transient projection, like different RCP runs, but snapshots at different levels of CO2, right?
Yes.
And when you did that, were you using a coupled ocean or somehow specified ocean SSTs?
I wasn't specifying an ocean. I'd have to go back and have another look.
So probably you're doing a coupled ocean. Is that what you're saying?
Yes.
Okay. One thing we found that if you do a coupled ocean run, usually for WACOM, CSM WACOM, we have to run at a much shorter time step to keep instability. And then the microphysics have issues with that. And then it ends up the model is not balanced. So maybe you want to check the redstone in the model, see if the energy is balanced in those runs.
Okay. Cool. I'll make a note of that. Thank you.
I have another question. If you go forward a slide or two, with this sort of population increasing with time. This one. is this increase due to collision, or is it just due to sort of launches and not having a sort of natural removal from objects re-entering?
Yes. So the launches were the same for each of the scenarios. So it wasn't that more launches were being added, but there is both a build-up of the number of objects like residing for a longer time, which is part of it, but also the amount of collisions actually happening were increasing. If I stop sharing briefly, I can try and find the I have a slide of that which I can show, which I should have added. It's very subtle. It's not many additional collision, like trackable, untrackable collisions happening. Here, yes, cool, right. If I share that and then go over here and share. Cool. Right, so on the left-hand side, we've got the trackable, untrackable, so that's the big events. And you can see over 100 years, say, as you step up in each RCP, you only get about one additional event happening over that whole 100 years. And it can happen at any point in that 100 years. But the big thing that was driving the increase in population was the trackable involved collisions. So that's the trackable on non-trackable collisions. And that was creating a lot more fragmentation, and a lot more objects were being created through that, and that was ramping up at a much faster rate.
Okay, thank you.
Yeah, I have a follow-up question on this. So in this scenario, when you do this calculation, do you have later the solar cycle change? I mean, solar activity change naturally, or is this a like solar minimum scenario or solar maximum scenario?
We was repeating solar cycles 23 and 24.
Oh, okay.
And we just kept looping through those. So
you mean alternate between alternate between 22 and 24?
Yes.
Okay.
So here you can kind of pick out the impact that has on the, actually, if I go to this one, you can pick out the solar cycle impact on the number of objects.
Mm-hmm.
So when it's more flatlining, that's during a solar maximum, sorry. Because those objects are being removed, but then as soon as you enter that solar minimum period, you get a rapid increase in the amount of objects again.
Wenbin, go ahead.
Yeah, in your earlier talk, you talked about the forecast, the thermosphere mass density.
Yeah.
So how far ahead of the time you do 3-day forecast or hour forecast? What's the accuracy of your forecast?
So that is something that we're currently quantifying much better. Day-long forecasts in the past pre-neutral densities were fairly good. I can't remember the numbers off the top of my head. But now, because we're running operationally at the Met Office, like behind closed doors, we're getting more data that will allow us to quantify that better.
Okay.
If that helps.
Thank you.
So we're working on a paper which will provide answers to that.
Okay, thank you. Looking forward to your paper.
Arvind?
Yeah, hi. Thanks for that walk. It was pretty interesting. I'm working on something similar for at least just daily tracking for a different purpose. We just want to monitor satellites and prevent interference with ground-based observations. But can you go back to the beginning of your presentation where you had that stuff with the TLEs?
Yes, let me just switch back to that one.
So while you're doing that, my question was actually with respect to the age of TLEs. Have you actually done some kind of comparative analysis where you take like a TLE that is from a certain epoch, and then you see if there is, I guess you see if there is the effect that you're hypothesizing? Can you actually see that if you use TLEs from different epochs? Like, so you take something from, say, solar maximum, and then you have something that's a week old, and then you take observations versus the propagation, and you see how well that sustains versus something that you do for the same age of TLEs, but during solar minimum or something.
Could you repeat that again? Sorry.
Essentially, propagating you're using the TLEs to seed a propagation model as well, right? Is that
Yes,
understand that
in a
right?
way, yeah.
And then and then you're checking with observations that you're taking from updated TLEs. Is that correct? Or are you looking at, when you're comparing them, are you looking at truth positions of the satellites once you want to compare whether they've aged because of?
Yeah, so we take the most current TLE and we assume that's true. Well, outliers removed. We assume that's true, and we look at the previous TLE and we work out how much drag that's experienced by deriving that, and then how much density it must have traveled through to actually result in that.
Right. And then have you noticed kind of solar cycle dependence for this, or any kind of periodic dependence of how bad the discrepancy is between TLEs that you download, the updated TLEs, and then the original TLEs that you use? So it's like a figure of merit or something like, okay, if you use it beyond a week, they're pretty much useless, or if they're 3 days old, they're useless, or something like that.
As in the gap between two different TLEs, and we're
Yes.
dividing them density.
Yes.
Right. Okay. Yes, I have, but I can't remember. Past 7 days, I think they're useless. Most people use 3 days because there's something in like the black box which is creating TLEs where they're doing a fitting over 3 days. So that's the optimal. I think you can get slightly more data out by going to 1 day. Just from the number of objects which are actually up there.
Okay, and that's independent of the time of year that you do this.
Yeah.
Okay, or I guess time in the solar cycle.
Yeah, so it's easier to pick out this when it's a higher solar activity, just because there's more drag, so there's more impact. But you can still pick out the changes, for example, at lower altitudes under low solar activity.
Okay, cool. Thank you.
Any other questions? Yes, no. So thank you again, Matt, for a nice presentation.
Thank you. Lots of good questions as well, so thank you.